Hello everyone, in this video we are gonna find the deflection of a beam under constant distributed loading. So the equation for deflection, we have y double prime mx ie. So our first step is to find this m, bending moment, as function of x. Here the reaction forces have already been determined. Even if it wasn't, we would have been able to find them using static equilibrium. Our first step is to make a section cut. And now we can keep the right or left side. Here I'm just gonna keep the right side. Right R1 or WL over 2. I have my distributed loading. And then I have my moment here. Moment at the cut location. The distance is x. And for this case, because our loading does not change, we only make one section cut. So here for us, x is simply between 0 and L. It could be anywhere. The loading does not change. So for this case, for our distributed loading, the magnitude of this is W, the length is x. So I'm going to write a summation of moment at the point of cut. Summation of moment at the point of cut. I'm going to assume counterclockwise to be positive. This load is creating a moment. It's going to be clockwise. So it's going to be negative WL over 2. The moment arm is x. My WX here would create a moment, and it's going to be counterclockwise. The moment arm here would be x over 2. It's acting in the middle of my segment, my cut segment. So positive WX, that's the magnitude of the force. The moment arm is x over 2. And that's all I have. I have MC, which is in the clockwise, counterclockwise direction, so it would be positive as well. If I rearrange it, my moment would be MCX WL over 2x minus half of WX squared. That's M. But if we go back to our equation, we need to take an integral to find slope. So finding slope would be y prime 1 over IE. I'll take it out of integral because they're constant. M dx. So IE, take an integral of this, would be WL over 2 x2 over 2 minus WX to the power of 3, 6. And I have an integration constant because I didn't use anything here. I didn't use a bound because I didn't want to find it at a particular location. If you want to find it, let's say at half in midway, you could write L over 2 here on the top, and then you find your slope at that location. But I wanted to keep it at x, so that means that it would be general. I can find the slope and deflection at any location. I find a general equation. The other important thing is that this integration constant C1 can be either inside this parenthesis or outside this parenthesis, whether it's multiplied by IE or not. It really doesn't matter. At the end, would be the same thing when you are applying boundary condition to find these constants. Well, let's go and find the deflection, which means that we have to take an additional integration. So WLX cubed would be 12 minus WX to the 4th, 24 plus C1X plus C2. I have two unknown, C1 and C2. I need to find them based on our boundary condition. What are the boundaries of the beam? The beginning and the end. We know at the beginning and the end, the deflection is 0. The slope, I can't judge about slope because it's not a clamped. If I was dealing with a clamped or a fixed, I could say that at this location, the slope would be 0. But for a simply supported case that we have here, all I know is that the deflection at the two ends would be 0. And that's all I have. So boundary condition tells me at x equals 0, y is 0. So if I plug in 0 here, everything 0, 0, and then y would be 0, that means that C2 has to be 0. The other condition is that x equals L, y again would be 0, no deflection. Here it would be a little bit more complicated. I have to put L and rearrange it, but at the end, trust me, that's what you get. Once I have C1 and C2, I have my deflection equation as well as the slope equation. So I have it based on x. So that means that I can plug any value and find the deflection and slope at any location. If the location of interest was somewhere in the middle, I can put L over 2 or 10 inch. If I had a gear here and I was interested in finding the deflection at this location, I can find it.